Have you ever wondered what electricity really is? It's not magic, it's science, and it all starts with incredibly tiny, almost unbelievably small particles. Everything around us, from the chair you're sitting on to the air you're breathing, is made of atoms. Inside these atoms are even smaller bits and pieces. One of the most important of these is the electron. An electron is a subatomic particle that carries a negative electrical charge. Think of it like a tiny, zippy ball of negative energy. These little guys are the superstars of electricity. They are what do all the moving. Now, every hero needs a counterpart, right? For the electron, that counterpart is the positron. A positron is what we call antimatter. It's the electron's twin, but with a twist. It has the exact same size and mass as an electron, but it carries a positive electrical charge instead of a negative one. So, where electrons are negative, positrons are positive. They are perfectly balanced opposites. While electrons are common and found in the atoms of everyday materials, positrons are much rarer. They are usually created in high-energy events, like those happening in particle accelerators or deep in space. So we have these two particles, the electron with its negative charge and the positron with its positive charge. In the world of physics, opposites attract. This means a negative charge will always be pulled toward a positive charge. It's a fundamental rule of the universe, like gravity pulling a ball back down to Earth. This attraction is the driving force behind everything electrical. It's this push and pull that we harness to power our phones, light up our homes, and run all the amazing gadgets we use every single day. Understanding this basic relationship is the first step to unlocking the secrets of electricity. It's not just about tiny particles, it's about their charges and how they interact. The electron is the key player we'll focus on because it's the particle that moves through the wires of our circuits. The positron helps us understand the concept of positive charge, which is crucial for defining the direction of electrical flow. So let's get ready to see how these electrons get moving and create the electrical current that powers our world. Consider it, science is cool. Now that we know about electrons, how do they create electricity? Imagine a wire is like a highway, but instead of being filled with cars, it's packed with electrons. In a material like copper, which is a great conductor, the electrons in the outer part of the atoms are not held very tightly. They are free to move around from atom to atom. When we connect a power source, like a battery, to this wire, we create an electrical field. This field acts like a giant set of traffic lights, telling all the electrons which way to go. It gives them a push. The battery has two ends, or terminals, a negative terminal and a positive terminal. Since electrons are negatively charged, they are repelled by the negative terminal and attracted to the positive terminal. This is that opposites attract rule in action. So the electrons start to flow, all moving in the same general direction, away from the negative end and toward the positive end. This organized movement of electrons is what we call electric current. It's not one electron racing from start to finish, but rather a slow collective drift, like a huge crowded line of people shuffling forward together. Interestingly, when early scientists like Benjamin Franklin started studying electricity, they didn't know about electrons. They guessed that the flow was made of positive charges moving from the positive terminal to the negative terminal. We call this idea conventional current. So, in circuit diagrams today, we still draw arrows showing the current flowing from positive to negative. Electron flow, the actual movement of electrons, goes the other way, from negative to positive. It's a historical quirk, but it's important to know both concepts exist. Think of it like this. If you have a tube completely filled with marbles and you push a new marble in one end, a marble will immediately pop out the other end. That's how current works. The effect is instant, even though each individual electron or marble only moves a tiny distance. This flow is what we measure in amperes or amps. The more electrons that pass a certain point in the wire each second, the higher the amperage. This flow is the workhorse of all our electronic devices, making things light up, spin, and compute. Let's dive deeper into how circuits work with a rule from a brilliant physicist named Gustav Kirchhoff. His first law, known as Kirchhoff's voltage law or KVL, is all about energy in a closed loop. The law states that if you travel around any complete circle or loop in a circuit, the sum of all the voltage gains must equal the sum of all the voltage drops. In simpler terms, all the electrical energy supplied by a power source, like a battery, must be used up by the components in that loop, like light bulbs or resistors. No energy is lost or magically created. Imagine you're on a roller coaster. The lift hill at the beginning gives your cart a bunch of potential energy. That's your voltage source, the battery. As you go through the loops, twists, and turns of the track, the components, you use up all that energy. By the time you get back to the station where you started, you're back at your original energy level. A circuit loop is just like that. The battery provides a voltage push, and each component, like a resistor or a light bulb, creates a voltage drop by using up some of that energy to do its job. Let's look at a simple example. Say we have a 9-volt battery connected in a loop to 2 resistors. The battery is our energy source, providing a gain of 9 volts. As the current flows through the first resistor, some of that voltage is used up. Let's say it's a 4-volt drop. Then, the current continues to the second resistor, which uses up the rest of the voltage, a 5-volt drop. If we add up the voltage drops, 4 volts plus 5 volts, we get 9 volts. The total voltage used by the components equals the total voltage supplied by the battery. The books are perfectly balanced. This law is incredibly useful for analyzing circuits. It helps engineers figure out how much voltage is being used by each part of a more complex device, like inside your television or computer. By applying KVL, they can ensure that each component gets the right amount of voltage to operate correctly without being overloaded. It's a fundamental rule of conservation of energy applied to the world of electronics. It guarantees that the energy we put into a circuit is fully accounted for as it does its work. Now for Kirchhoff's second amazing rule, which is all about how current behaves when it comes to a fork in the road. This one is called Kirchhoff's current law, or KCL. This law deals with junctions, which are points in a circuit where multiple wires connect. KCL states that the total amount of current flowing into a junction must be equal to the total amount of current flowing out of that junction. Think about it. Electrons can't just vanish into thin air or be created out of nowhere at a connection point. Every electron that enters has to leave. Let's use a water pipe analogy, which is great for understanding current. Imagine you have a large water pipe that splits into 2 smaller pipes. The amount of water flowing into that split has to be the same as the total amount of water flowing out through the 2 smaller pipes combined. Water doesn't just disappear at the junction. Electric current behaves in the exact same way. The junction is simply a point where the path for the electrons divides, so the flow of electrons splits up to travel down the different paths available to them. Here's a practical example with numbers. Let's say we have a wire carrying 3 amps of current that flows into a junction. At this junction, the wire splits into 2 separate branches. If we measure the current in one of the outgoing branches and find that it is 2 amps, then KCL tells us exactly what the current in the other branch must be. The total current coming in, 3 amps, must equal the total current going out. Since we already have 2 amps going out one way, the remaining current, 1 amp, must be flowing out through the second branch, because 2 amps plus 1 amp equals 3 amps. This principle is essential for designing parallel circuits, which are incredibly common in household wiring. All the outlets in a room are typically wired in parallel. This means the main current from the breaker box splits up to power each outlet. KCL helps electricians and engineers calculate how much current each branch will draw and ensure that the main wire is thick enough to handle the total combined current without overheating. It's a simple but powerful rule of conservation that ensures our circuits are safe, balanced, and predictable. Science is all about rules, and these rules make things work.